So we'll get this whole thing recorded and uploaded to YouTube in fairly short order. So if you have to, dip out at some point, no big deal. The recordings will hopefully work. So anyway, I'm gonna go ahead and get started. So thanks so much, everybody, for joining in. So this is our first ever virtual workshop on molecular cavity quantum electrodynamics. And what I'm only going to spend a few minutes on these slides. I'm going to spend most of today on my tablet. I'll just give a kind of really quick motivation to things. But for the most part, we really want to focus on the formalism today and kind of work through it slowly, at least as slowly as we can in 3 hours. So not everything will be done totally explicitly, but we'll try to do a decent job. So I'll be doing all of this today on my tablet, and then tomorrow, me and Ruby Manderna and Peyton Roden, two graduate students in my group, will be doing a live coding session. So the idea really is today we're going to try to work through where you would come up with a Hamiltonian for a molecule strongly coupled to quantized light modes in a cavity, such as you see here, and then come up with some expressions that we can implement as Python code tomorrow. And so that's basically the goal. Now, we're going to do this in a way that is relatively reasonable. So what we're going to do is consider the molecule. We're going to consider the vibrational structure of the molecule within the harmonic approximation, and we'll have it coupled to a single quantized cavity mode. And so that'll be about the simplest way that we can approach this while still maintaining essentially all of the sort of formal rigor of this approach of molecular cavity quantum electrodynamics. But this is an area that my group is pretty interested in, and usually we're actually thinking about electrons coupled to these quantized cavity modes, and thinking about many interacting electrons coupled to these quantized cavity modes. And so that really will follow the same formalism, but also will be much more challenging to actually implement practically. But this is a kind of a schematic picture of this idea. And then I want to also acknowledge, so we're going to be using some notes that our group has developed, and also this example that we've also developed, and we ended up putting this into some project called the ACS Digital Primer series. So that's out. There's a chance your library might subscribe to that series, but maybe not. And if you really are interested in learning more, I do want to recommend you take a peek at it. And if you feel so inclined, you can ask your library to purchase a copy. I think it's like $40. But yeah, with that said, so most of the group has worked on these notes, and so I definitely want to acknowledge those group members. And so this is the group: Kenny, Nam, Ruby, Peyton. So Ruby and Peyton will be doing the live coding with us tomorrow. Elijah was an RU student over the summer, and I'm not showing you Shaye, Austin, or Lane. Lane is an alum who helped us with the notes as well. And Austin and Shaye are undergrads in the group. So all have contributed in different ways to this. Okay, so really quick, I'll just show a couple of slides for motivation, and then we're going to switch to the tablet. So now we're going to be talking about molecules strongly coupled to light. There's a lot of different applications or reasons why you might care about this. This is not exhaustive, but basically the area that my group got interested in that led us down this path was in this area of so-called polariton chemistry. So here's a little movie that all of the polariton folks show. What is a polariton? Well, it's any kind of material excitation which is strongly coupled to some kind of photonic excitation. So here the photonic excitation is this object called an optical cavity, which are these two mirrors, and the photonic excitation would be basically the addition of photons into this cavity. So like the ground state of the cavity, let me pause, would be an empty cavity, and then the first excited state would be a single photon in the cavity, the second excited state would be 2 photons, and so on. And then the molecule is this sort of 2-level system represented here, and it can be in the ground state or the first excited state. And so the polariton results when the sort of the energy of these two systems match, and so they're primed to exchange energy very readily. And so if the interaction strength is really large, that means they exchange energy very rapidly. And you sort of lose the ability to sort of say, where is the energy? You can't really say that the energy is sort of in a cavity occupation state. You can't really say that the photon, there's a single photon occupying the cavity, because the molecule could be sucking up the photon and becoming excited. You can't really say that the molecule has become excited, because the molecule may be giving the photon back to the cavity. And so that energy exchange is so rapid on all other time scales that you basically have to resort to calling this sort of thing some kind of hybrid quantum state, which we call polariton. And very, very quickly, the interest in this in the chemistry community has been quite robust in the last decade or so, because people have realized that if you create the conditions of strong coupling, you can change chemistry. So this was sort of the first chemical reaction where people took this large organic molecule that has an isomerization, and they coupled a cavity confined photon to the first excited state transition of this species, which has a visible absorption feature. And that sort of altered the potential energy surfaces that led to isomerization and slowed the whole reaction down. The reason for this is that anytime you create a polariton, you sort of split the one excited state of your molecule into 2 excited states, and those excited states are no longer molecular only, they involve light character as well. And this is true if you're talking about electronic excitations or vibrational excitations or otherwise. And so if you think about creating these kinds of polariton states by electronic strong coupling along some potential energy surface, there'll be regions of the potential energy surface that are sort of maximally split and that have maximal polariton character. But importantly, those potential energy surfaces that emerge are new potential energy surfaces, and that sort of changes the way that chemistry can happen. And then I'll skip down to something that's sort of even more recently been appreciated, that you don't even have to necessarily couple this confined photon to any transition at all. Just the strong interaction with the field associated with the photon is enough to sort of rearrange electron density, which can actually lead to changing chemistry on the ground state of a molecule. And this is an example that just sort of theoretically predicted recently of changing the substitution preference of this nitrobenzene molecule through the orientation of some kind of confined cavity mode. So those are just some of the examples, and like I said, what I really want to do is actually just focus on the formalism, and the idea really for that is just that we feel that there's a lot that chemists are sort of well poised to understand about these kind of phenomena, and yet if you just try to dive in, some of the things look a bit unfamiliar because there's this sort of language of cavity quantum electrodynamics or quantum optics or things like this. But this language is really not that inaccessible to chemists, and so we just wanted to, really try to drive that point home. And so here we are, and now I'm going to try to share my tablet notes and really jump into things. Okay. All right. So I can confirm on the screen that I see my tablet notes. If you don't see an outline, can you please put up a remark like a red X or something like that? It indicates you can't see my notes. And otherwise, we will assume that you can. I also want to point out, so like I said, Peyton and Ruby are both here. I'm going to try to pause from time to time for a little bit of Q&A or discussion, but I do encourage you, if you have a question, of maybe first trying to chat Ruby and Peyton, and if it warrants sort of pausing and breaking into discussion, then they can let me know, and we can stop and have the discussion. I don't want to. We don't really know exactly how long this is going to take, so we're going to be here till 5 or at the latest. So I'll try to prioritize actually making through the content. All right. So here's the outline. I'm going to start by trying to just quickly draw a physical picture for this simple model. So tomorrow we'll actually have sort of the parameters of this model, which is a hydrogen fluoride molecule coupled to a cavity mode. And the idea will be that the cavity mode that it's coupled to is going to be tuned to the fundamental transition of HF. So the first vibrational transition of HF. And we're going to use the harmonic approximation. So really it's tuned to any vibrational transition between two adjacent states and HF. But we'll just think about the fundamental. All right, so we'll do a brief reminder of the harmonic oscillator model and the ladder operator formalism. And honestly, this is, that's really the sort of the heart of the language that we're going to use for cqed, is basically the harmonic oscillator and the ladder operator formalism. So we'll spend a little bit of time just writing down that for HF, for the molecule, and try to make some connections to the molecular properties. So we'll think about the force constant and the reduced mass, and then we'll also try to think about sort of the effective charge of the molecule, of the HF molecule, which is how in one representation we're actually going to couple to the field. And then in the other representation, we're going to actually couple through the dipole moment. And so we'll make the connection between the effective charge and the dipole moment. Next, we'll make some remarks about the language for quantized electromagnetic fields. So this is not going to be a comprehensive treatment of quantized radiation fields, but I'm going to try to make the connection again to the harmonic oscillator, because basically we are thinking of these quantized radiation modes as quantum harmonic oscillator states. And that is essentially because the electric and magnetic fields are basically obey a harmonic oscillator equation of motion. And the energy states of these quantized radiation modes follow the harmonic oscillator ladder. And so consequently, the kind of observables that of the electromagnetic field in this kind of ideal cavity mode, they have operators like the electric field operator, which I'm denoting E hat, and the vector potential operator, which I'm denoting A hat. Those are the ones that we'll actually use, but there's other ones like the magnetic field operator and so on that can be expressed in very similar ways as the position and the momentum operators in the harmonic oscillator, and that's not an accident. So we'll discuss that, and that is going to set us up basically for our two sort of non-interacting Hamiltonians, right? A non-interacting Hamiltonian for the matter is going to be the harmonic oscillator. The non-interacting Hamiltonian for the light is going to be a harmonic oscillator. And then we have to deal with the interaction. So the first way we'll write that down is through this so-called minimal coupling Hamiltonian. And we'll write down sort of the general form of that minimal coupling Hamiltonian, which would be, valid for sort of any material coupled to a single photon mode in principle. And then we'll just kind of quickly figure out how to prune that down for the specific case that we're dealing with the quantized radiation field coupled to the vibrational structure of a molecule within the harmonic approximation. And that is going to show up particularly as the interaction between the momentum operator of the molecule and the vector potential operator for the light field. And I find this this doesn't really ring with any kind of intuition I naturally have as a chemist. So I will try to insert just a little bit of dimensional analysis to sort of help ground that coupling and try to get at what it means. And then what we'll do ultimately is transform our representation to one that I think rings a little bit more with my intuition as a chemist, which is that we can come up with an equivalent representation where it's actually the dipole moment of the molecule, which is coupled now to the electric field of the quantized radiation mode. And we'll actually do two transformations. And the first will get us to that coupling between the dipole moment and the electric field. And then the second is actually going to get us to the dipole moment back to the vector potential. So we'll go through both of those because those are, again, a common part of the language. The transformations that we'll do are called unitary transformations. And again, we'll try to show just a few basic properties of those things and how we actually deal with them. And then the very last thing I'll remark on, I guess, we'll see how much time is left to remark on this, but is now that we have sort of the coupled Hamiltonian and a few different representations, I'll try to remark briefly about how we're going to actually, think about finding the energy eigenstates of these Hamiltonians in a tensor product basis. So we'll talk a little bit about those tensor product states and the tensor product of the Hamiltonian matrices. So that's the plan. Let me first off, I want to turn off my camera. Now get myself organized. Okay. So let me drag this down. All right, so I'm going to just try to draw a real rough sketch of what we're thinking about. All right, so I've got this optical cavity, which again, I'm just going to think about as basically two parallel mirrors. And this cavity is going to confine light. So it's basically going to, permit these sort of like, standing waves of light in it. And so if I have the electric field associated with one of those, some photon in the cavity, one of the things that I can realize is that the electric field in this cavity is going to point along a particular direction. And so I'm just going to notate here that I've got some electric field pointing along this direction. And actually, it turns out that the other quantity that we'll be interested in, right, the vector potential, is also going to point along the same direction. So I've got some vector that's sort of pointing straight up, and maybe I want to call that the z-axis, just for lack of better term, and I don't know, this is the x-axis. Okay, so this is my cavity, and again, I can think about the energy states of this cavity, and I'm going to discuss all of this in a little bit more detail later, but I can think about the empty cavity, which I'm going to call the quantum state associated with the empty cavity. I'll call the 0 ket, and the 1 ket would be the cavity with one photon in it, and there's really infinite number of these occupation states. So in general, I'll just call these by the number of photons occupying the cavity. And I'm going to try to do this as well, because we're going to use a pretty similar notation for the quantum states of the of our molecule. So let me just insert this little superscript C, okay, to denote cavity states. And then, the energy difference between these cavity states is just going to be given by Planck's constant times the cavity frequency, which I'll call omega C, right? So. Okay. And I'll call these occupation states. Okay, and we'll sort of write down the energy eigenvalue expression for these occupation states in a few minutes or so. Okay, so now so each one of these photon occupation states, right, is going to have some electric field associated with it, some vector potential associated with it. It's going to point along this z-axis. And so now if I have a molecule like my HF molecule, so I'm going to draw HF, and I'm going to draw HF in a way so that its internuclear axis is also pointing along the z direction, right? And so there's a few things that I can associate with this z direction now if the molecule is pointing along this direction, okay? And so importantly, one thing is that there is going to be a dipole moment associated with HF, and it's going to point along the z-axis. And so that'll be important for how we think about the coupling to the electric field shortly. But the other thing is that if I really zoom in on this F atom, for example, oops. I can think about the vibrational motion of the of this HF molecule, right, is having displacements along the z-axis as well, and that means that both the displacement coordinate of HF and the momentum coordinate is also going to point along z. And so I'll just write the p hat vector and the x hat vector associated with HF. They're both going to point along that z-axis as well. And the p hat vector in particular, we're going to see, is going to be quite important to how it couples to how the molecule couples to the vector potential. Okay. And again, all right, so I can think about the energy eigenstates of the HF molecule. And again, I'm going to have this kind of same kind of picture. So let me use a color over here. And I guess if I'm using superscript C for the cavity, I'm going to use superscript M for the matter states. And so, I have these set of quantized energy states, which again, we'll write a little bit more explicitly for the molecule as well. And the energy difference between any two of these states is going to be equal to h bar omega sub m. Okay. All right. So that's kind of the physical picture. And I guess what we ultimately want to come up with, right, is if I got, think almost like some kind of linear combination of atomic orbital kind of picture, right? I've got these two states for the molecule, for example, and I've got these two states for the cavity if they're in resonance, and there's some interaction, right? Then what I might expect is, well, number one, I'd have kind of like these uncoupled states, which I'm gonna draw like so. So in my sort of dotted dash lines, right, I can have these uncoupled states like 0M and 0C. Right, so both an empty cavity and a molecule and the vibrational ground state. And then, you know, perhaps this state here is like 1M and 0C. And then perhaps this state right here is like 1C and 0M. And then, you know, this state here would be 1M, 1C. Okay, so that would be sort of like the uncoupled picture, right? No interaction, but just the sort of the you know, accounting of the of these possible composite energy states. But if there's an interaction, what I expect is I'm actually going to get you know, some new states, right? One raising in energy and one lowering energy relative to these 1, 1, 0 and 0, 1 states, right? And in fact, we'll call these states specifically the lower and upper polariton states. And it turns out that, right, these states, they're going to be linear combinations of the excitation from the 0 matter state to the 1 matter state, and the excitation from the 0 photon state to the 1 photon state, or 0 cavity state to 1 cavity state. So they're going to kind of mix in this material excitation or matter excitation with a photon excitation. And that's going to be sort of the defining kind of characteristic of our polariton states. Okay. So so let me just pause there just to see if any pressing questions so far before we actually start reminding ourselves of the kind of the harmonic oscillator model and then the cavity quantized model. Okay. You know, the other thing I meant to do is turn on this AI companion. I'm going to go ahead and do that. Okay. All right. So let's continue then. All right. So that's kind of the physical picture. And then what we're going to ultimately try to do is have a Hamiltonian that's going to give us access to the precise energies of these lower and upper polariton states, and also the ground state and this you know, additional excited states. So so that's the goal. Okay. All right. Now let's go to the next bullet point, which is we're gonna remind ourselves of the harmonic oscillator. All right. So what I'm gonna do is I'm gonna write now the harmonic oscillator Hamiltonian in a few different ways. And let's start this way. So, and this is going to be for our molecule. So I'm going to use now the subscript M. Okay. So my Hamiltonian for the harmonic oscillator, I'm going to write as minus h bar squared over 2 times the reduced mass, d squared dx squared plus 1/2 kx squared. And what I will also do is let me draw a little schematic of my HF molecule. Actually, let me draw a schematic of the potential. That's what I actually want to do first. All right. So this is my potential. And essentially what K is, right? K we call the force constant. So force constant is essentially one of the kind of key parameters of the harmonic oscillator model, and the other parameter of significant importance is the reduced mass. Okay, so if I've got my HF molecule and I, want to think about HF molecule in this kind of, Hookean way, right? The K spring constant is that's kind of the intuition, right? The larger the K, the stiffer this bond is, the harder it is to stretch it. And the steeper this potential is. And the smaller K is, right, the looser the spring constant is, the easier it is to stretch, and the sort of wider the potential is. And then the reduced mass is just nothing more than the mass of hydrogen times mass of fluorine over mass of hydrogen plus mass of fluorine. And so when we do this tomorrow, we're going to have a value of K in atomic units and a value of the reduced mass in atomic units already set for us. And if you've already looked at the notebook, you've seen that. Okay, and so now the other thing, right, is this model. We can write down our expression for the energy eigenstates of this model, which again, I'm just gonna notate with these NCATs. So right, so this is our energy eigenvalue expression for the harmonic oscillator. So this is how I'll notate the energy eigenstates. And then big pop quiz time. Everybody's waiting for it. How do I find this frequency for the harmonic oscillator? Someone chatted in. No chats. All right, I'll wait 5 more seconds, then I'll write it. One new message. H bar. So how I'll get the frequency is actually I should have maybe clarified my question. What I want to do is I want to find a way to express the frequency in terms of the parameters of this molecule. So all I really need to know about this molecule to get the frequency is the force constant K and the reduced mass mu. So this is actually all I need. This is one of the things that, yeah, there we go. All right. Yes, that 1/2 pi, by the way, I'm going to be using omega, right? This angular frequency. If you prefer the non-angular frequency, right, nu, then that's exactly the expression that you would use that Rajanya just chatted. So these are totally fine, right? And how do I relate nu to energy? E is equal to h, ordinary Planck's constant, times nu sub m. And if I want to use the angular frequency, E is going to be the relationship between frequency and energy for angular frequency is h bar omega sub m. Okay. Right. So beautiful thing about the harmonic oscillator, if I know how stiff the bond is and I know the reduced mass, I can get this omega, and that tells me basically about the entire vibrational spectrum of this molecule within the harmonic approximation. Okay, so in particular, right, I see and have this expression up here in terms of these quantum numbers n, and those quantum numbers can be any integer, any positive integer, right? And so the ground state is the one with n equals 0, and so I would just write basically the energy of state 0, right, is going to be h bar omega sub m times 0 plus 1/2, right? So that's basically h bar omega sub m over 2, right? And then there's a state which we'll call the state 1 ket, and its energy we'll call E1, and that's equal to 3/2 h bar omega m, and so on. So this is all fine. What I want to do also is I want to express this Hamiltonian in a few different ways, right? And so so the other way I want to express this Hamiltonian is, so let's grab this thing, give myself a little room. Is I can also set this thing equal to the momentum operator, p squared over 2 times mu plus 1/2 k x squared. And this is just a reminder. So let me put this up in here, right? What's the definition of p hat? It's equal to minus I h bar d dx, right? So indeed, if I take p hat and square it and divide it by 2 mu, I will in fact get minus h bar squared over 2 mu d squared dx squared. All right. And the other thing that so we'll sort of, for whatever reason, we have implemented our code with slightly different but equivalent notation. So the last thing I'll say is that you can, using the definition of K, I can also write the potential in the following way. And that's going to have a sub m x hat squared. So these are all equivalent ways to write the harmonic oscillator Hamiltonian, and I will even write down another way using the ladder operators in just a minute. But importantly, right, I think the thing to emphasize is that both, oops, sorry about that. Right. Is that thank you for asking this question. So let's see, h sub m bar and ER is the same. So let's see, they are not the same. So and let me know if this doesn't address your question. So so there's two things we have going on here, right? So we have h hat sub m as an operator, and specifically, what kind of operator is it? This is an energy operator. Okay, but And so now if you happen to take your energy operator and act on a special state like the energy eigenstate, what you'll get back is an energy eigenvalue times that state. And so in that special circumstance, right, what you have is an equality on the left-hand side. An operator acting on a state will give you the same state back, scaled by a number, and that number will specifically be an energy value. But more broadly speaking, the energy operator is not the energy. It is an operator which relates to the energy. And you can use the energy operator in a variety of ways to either get energy eigenvalues or to get the average expected energy of a particular state. Did that address your question? Okay. Okay, great. Thank you so much. Yeah, so importantly, all these different ways of expressing the Hamiltonian, you can ultimately see that your operator, your Hamiltonian operator, has got a p squared plus an x squared, and some constants. So it's quadratic in both the momentum operator and the position operator. Okay, and so what I also want to introduce at this point is a set of related operators, which we'll call the ladder operators. And we're going to have ladder operators for both our matter subsystem and for our cavity subsystem. And I'm going to use different letters for these. And I'm going to try to, as best as I can, to consistently use A dagger and A. So this one is A dagger. And this one is A, or A hat. I should call them A hat and A hat dagger. And the A and A daggers will be matter operators. And when we introduce these operators again for the cavity, I'm going to call them B and B dagger. And they're going to have identical properties, but I just want to distinguish between the ones that are acting on the matter subsystem with A's and the ones that are acting on the cavity subsystem with B's. Okay. So there's a number of ways that you can go about thinking about the ladder operator, and I'm going to try to start with kind of the intuitive one. And so let me just grab my potential again, and let's think about this thing. Okay, so let's imagine I've got a molecule and it's in state 0. And what I do is I act upon state 0 with A dagger. And I probably should have said this before. Let's write this down right to the side. A dagger is the raising operator. And A is the lowering operator. While we're at it, if you've studied the raising and lowering operator formalism before, give it a green check mark. And I'm just curious to take a quick survey of who has seen this before. All right, so I can think about Maybe not a tremendous number of people. Okay. So that's okay. It's not too complicated. Okay, so let's think about what this thing does. So the raising operator, what it's going to do is raise my quantum state by 1. So I'm going to think about this thing taking me from the 0 ket up to the 1 ket. Okay, so that's the action of a dagger on 0, is it's going to give me out state 1 sub m. Okay. Let's repeat this because it's actually important to see where this goes if I continue, right? So this is now, so I've applied the raising operator to the 0 ket and I've gotten the 1 ket out. Now let's imagine that, so it takes me up to the 1 ket. Now I've got another state above this, right? So this is 0. This is 1. This is 2, and so on. Okay, so now if I apply a dagger to the 1 ket, I'm going to get, it's going to raise me again to the 2 ket, but something else is going to happen. I'm actually also going to get a factor of the square root of 2. Okay. And let's just keep it going. And I'm going to ask another quiz question. All right. So what I'm going to do, right, let's imagine I've raised myself now twice. So I'm in the 2 ket and I'm going to raise again. I'm going to keep raising, right? So I'm definitely going to go to which ket if I raise? Yes, I'm going to go to the 3 ket. And I'm going to get another numerical factor outside of that 3 ket. Does anybody have an idea what it should be? Square root of 3. All right, I see Arthur is the first one to chat in the right answer. Square root of 3. So in general, what I can say, let me just try to write down a general expression, right? I can take the raising operator, a dagger, and act on any ket. And what I'm going to get back is a ket whose quantum number has increased by 1. And I'm going to scale it also by a factor of square root of n plus 1. So if I'm in ket 0 and I raise it, I'm going to get square root of 1 times ket 1. If I'm in ket 1 and I raise it, I'm going to get square root of 2 times ket 2. If I'm in 2 and I raise it, I'm going to get square root of 3 times ket 3. Okay. So that's the raising operator. This is sort of the important relationship we have for the raising operator. And the lowering operator is going to do basically the reverse operation. So let's copy this thing. All right. So oops. All right, I'm going to start from 3. And so a hat on 3m is going to give me back square root of 3 times 2m. So it's going to take me down, and it's going to pull out a factor of the square root of n, where n is the state that I was in, right? So if I do square root of a hat acting on 2m, I'm going to get square root of 2, 1m out, right? So my relationship for the lowering operator, I apologize for being a little bit quicker with this one, but I hope now the idea is a little bit more familiar. Okay, so these are the relationships. Now, there's a limit to how much you can lower. You cannot lower beyond 0. So if you apply the lowering operator to the 0 ket, you basically destroy your system. You can't lower below the ground state. You can keep raising to your heart's content. There's no limit because there are an infinite number of harmonic oscillator states. So this is the behavior of the ladder operators. And now, importantly, what happens is if I apply them in sequence, okay? So let's try to take these rules, and we're kind of coming up to an hour, so I think it would be a good idea for you all, for this to be like one little pause where you try to work this out yourself, particularly if you've never worked with these before. So what I'm going to do, right, is I'm going to give myself a state, and I'm going to give myself the state 3, the 3 ket, right? So now this is the third excited state of the harmonic oscillator. And what I'm going to do to it is I'm going to apply the lowering operator to it first. And then after I've done that, I'm going to apply the raising operator to it, okay? So I'm going to take this A dagger A, and I'm going to act with A hat first, which is going to give me some new ket. And some numerical factor. And then I'm going to act with a dagger second, which is going to give me a new ket and a factor, a numerical factor. Okay, and so what's the result, right? So it's some ket, some number, and some ket. And what I want to do at this point is I'll just pause the recording, and let's take a quick 5-minute break. And when we come back at exactly 3 o'clock Eastern time, you can chat your answer if you would like to. And I will reveal the answer just after 3 o'clock. So we'll keep it quick so we can keep moving along, but try to work that out on your own if you've never used these before. Okay. Start the recording again. Great. All right. So got pretty good participation on this poll, and actually pretty good convergence towards the correct answer. So, yeah, basically the correct answer is 3 times the 3 ket. And let me just try to quickly work out why that is. So just remember the rules that you have, right? What's the lowering operator going to do? Well, it's going to take you down 1 ket, but it's actually going to pull out. So if you're in ket 3, right, the lowering operator is going to take you to ket 2, but it's going to pull out a square root of 3, right? So let's do that one first. So this is going to give me a dagger, which I haven't acted on yet, times square root of 3 times 2 ket. Okay, and now I can shift my number over to the left so that I have the operator acting on 2 ket, right? So this is the same thing as square root of 3 times a dagger acting on 2 ket. And this a dagger acting on 2 ket, right? What does a dagger do? It's supposed to give me square root of n plus 1 times ket n plus 1. So I've got ket 2, so square root of n plus 1 will be square root of 3 again. So I've got a square root of 3 times the square root of 3 times a 3 ket, which is the same thing as 3 times 3 ket. Okay. Now, we're almost done with the harmonic oscillator. What I want to do at this point is point out to you that, and you can get to this in a variety of different ways, but one way is sort of observationally to notice that what happens when you apply a dagger A on your harmonic oscillator states, it basically pulls out the quantum number, right? So you get the same state just scaled by its quantum number. And so that means, okay, the states n sub superscript m, right? These are eigenstates of the operator string a dagger A, and their eigenvalues are their quantum number. So a dagger A is sometimes called the number operator. And importantly, if we go back to the energy eigenvalue of the harmonic oscillator here, right? This is the expression for the energy eigenvalue. We can see that basically it's a constant multiplied by the quantum number plus 1/2. So we can actually see that we can express the Hamiltonian operator in terms of the number operator. Okay, so this is actually yet another equivalent way of expressing the Hamiltonian operator, which is to say, I'm going to have Planck's constant times omega sub m, the frequency, multiplied by the operator that gives me the quantum number, or the number operator, plus the constant 1/2. Okay. So this is yet another equivalent way of expressing harmonic oscillator Hamiltonian. Was this the fourth way? And this also can be derived from the following relationships. So I actually can go a little bit further with these ladder operators. And so I can actually take the position and the momentum operators and express them in terms of ladder operators. So that's one of the last things I want to do is if I take the position operator for my harmonic oscillator, I can actually express it as Planck's constant over 2 over the reduced mass times the frequency times the sum of the ladder operators, so A dagger plus A. And similarly, the momentum operator I can express as the imaginary unit I times square root of mu h bar omega over 2 times the difference between the raising and the lowering operator. And you can invert these relationships so that you can actually express your A dagger and A in terms of position and momentum. Some of these relationships we're going to make use of in the future, so I want to write them down at this point. And I want to make, finally, a few more remarks about the properties of these operators. Which will also be important. So, oops, mu omega, sorry. Okay. All right, so these are relationships between the position operator and the momentum operator and the ladder operators. Now, x hat and p hat are Hermitian operators, so there are observables that correspond to position and momentum. On the other hand, the raising and lowering operators are not Hermitian. But they are the adjoints of each other. So you could confirm this by using the fact that Hermitian operators are equal to their own adjoints, and then taking, for example, the adjoint of this expression. Gives this. Okay, so what does this mean? Okay, the raising and lowering operators, they're not Hermitian. They don't correspond to any observables. They're still quite useful, and the string of some certain strings of them will be Hermitian. So for example, A dagger times A is Hermitian, and A dagger plus A is Hermitian, and A dagger minus A is Hermitian. Very last property that I want to remark. So, and all of these, I would really encourage you to spend some time, if you like this kind of stuff, spending some time confirming sort of the consistency of all of these things that I'm telling you. Even though I'm not going to have time to go into it right now, but you can take as an example this canonical commutation relation between position and momentum, which is equal to I h bar. And then use the relationships between x hat and p hat and A dagger to show that, in fact, A and A dagger have some very interesting commutation relations. And let me just remind everybody, right? Commutator means I'm going to do operators in this order. Commutator x and p means I'm going to take x acting on p and subtract from a p acting on x. And the result of that is equal to IH bar. And so here, right, what this means is if I have a dagger acting on A minus A acting on A dagger, then that's equal to -1. Oops, I did this wrong, sorry. This one is +1. Okay. So let me pause for just a second because that kind of wraps up the harmonic oscillator for the matter subsystem and the kind of an alternative way to express that Hamiltonian in terms of the ladder operators and then some of the key relationships we'll need for the ladder operators moving forward. So any questions before? Am I still screen sharing? I am still screen sharing, Nor. Is anybody else running into this problem? They can't see my notes?
Yeah, I still can't see them, so I'm not sure if it's just something on my end or yeah.
Okay. Is anybody else not seeing it?
Yeah, I was having this problem before. I think we just need to switch the view in
Okay.
the Zoom call. Not you, I mean, whoever is having this problem.
Then Nor, you may need to switch the view.
Yeah.
Okay, I'll give that a try. Thank you.
No problem.
Yep.
And I will also just once this is all done, I'll also link these notes to the Google Doc that has everything.
Oh, perfect. Sounds good.
Okay. Now I'm not sharing, I'm sharing something else. Okay. So let's move forward to the next bullet point. And so, okay, just make sure there's no other questions. Any other questions before I move to the next bullet point? All right. Let me grab the next bullet point then. So, no, not, sorry, not quite. We have to do this, the Z effective, but I'm going to do this once we get to the coupling. Okay. But it's very important. So I think everything else is done. All right. So let me copy this. All right. So the quantized radiation field. So, thank you, Kenny. Okay. So what I want to, let me grab my picture too, sorry. I hope this isn't giving everybody whiplash where I'm going back and forth and copying and pasting things like this. Okay. All right. So this is again now this kind of picture of you know, my standing wave in my cavity where I've got my cavity boundaries here. So I'll call this mirror 2, mirror 1. And actually this kind of like standing wave picture is a kind of a classical picture. The quantized picture, the quantum mechanics picture, right? What I really have, well, I don't know if I really have. No, I don't really have that, right? Wave functions are not real. But you know, our formalism suggests, right, what I have these wave functions for my different photon states, and in fact they, you know, basically look like this is supposed to look like the wave function for the zero cavity state, and that's meant to look like a Gaussian, which is sort of the functional form we have for the ground state of which system, everybody? I'm going to start writing it very slowly. Awesome. Thank you, Arthur. Yeah. So I won't really refer to any kind of functional representation of these states in this talk, but if you wanted to have them, right, and you remember what the solutions to your harmonic oscillator system looks like, right? The ground state is a Gaussian, the first excited state is a Gaussian times a first order Hermite polynomial, and second excited states Gaussian times a second order Hermite polynomial, and blah 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 blah, and each one introduces a node and so on. So so this is all to say that the cavity states are also themselves harmonic oscillator states. And so we can actually write down for the cavity a Hamiltonian, which is exactly a harmonic oscillator Hamiltonian. So I'm going to write that right now as h hat sub c is equal to, now I'll call it h bar omega sub c for the cavity times b dagger times b. Now remember, these b daggers are exactly the same operators as a daggers. I'm just giving them a different label, right? So that we know that they act on the cavity system, okay? Well, I say that they're exactly the same. They're almost exactly the same. I'm going to point out one teeny tiny difference. And I'm going to do so superficially because this is a difference I don't have the depth to really understand, but I'll point it out nonetheless. Okay, but here's the idea, right? Is that what do these B daggers and B's do? Well, the B lowers cavity occupation. And returns a numerical factor. So exactly the same rules as before. So you can think of B as removing a photon and B dagger as raises the cavity occupation. Right, and B dagger adds a photon. So B dagger will remove a photon from the cavity. B dagger will add a photon to the cavity. Okay, and so now what's the difference? I'm oh, okay, sorry, I'm missing one little thing here. Just adding this 1/2, which I'm going to put a little label up here. ZPE, 0-point energy. So both the ground state of the harmonic oscillator and the ground state of the cavity, right? Their energy isn't 0. It's h bar omega over 2. That's called the 0-point energy. You will often find in the literature that people just leave that 0-point energy off. We do that sometimes. Sometimes it's convenient to do that. But it is there. So that means that the cavity, even without a photon in it, has some energy in it. It has energy of half the frequency of whatever the photon that would fit in it is times Planck's constant. Okay, so I rather like the interpretation of the raising and lowering operators for the cavity because they add photons or take them away, and I think that's quite intuitive compared to the harmonic oscillator, in my humble opinion. Okay, and the last thing that I wanted to say, right, is that, well, the other thing I wanted to say really quickly is we can absolutely think about a momentum operator for the photon in the cavity and the position operator for the photon in the cavity, much like we thought about them for the harmonic oscillator. And we can express these things in terms of our B daggers and B's. And how we do that is as follows. So for the momentum operator, I'm going to have the same factors except for no mass. There's no mass here. And that's the thing that I wish I could really justify in my simple-minded way of thinking about things, that photons are massless, so I guess it makes sense they don't have mass, but I've heard things about photons having mass, so I just don't know. But you'll notice that otherwise these operators have the same prefactors as they do for the harmonic oscillator, except for no mass. That's the main point I wanted to raise. And they're still Hermitian. Okay, so the momentum operator for the cavity is still a Hermitian operator. The position operator for the cavity is still a Hermitian operator. And they still obey the same commutation relations. So I can have the cavity position operator commutator with the cavity momentum operator gives me IH bar. And then the B daggers and B's have the same commutation relations as well. Okay. And the last thing, so we'll mention this last thing. So the photon, in addition to having observables like position and momentum, also has these other observables that we don't really think about for the molecule. It has an electric field, it has a magnetic field, it has a vector potential. And so we can actually express those, since those are things that you can observe for the photon, they have operators associated with that. So one of the reasons I won't be using any E hat operators for the energy operator is because I need an E hat operator for the electric field. So let me just put below, this is the electric field operator. It's not the energy operator. All right, and what the electric field operator is, I'm going to write this a few different ways. I'm going to write it with an I, the imaginary unit again, times an E naught, where this thing is a vector, B dagger minus B. And interestingly, if I look at, I have to give you a definition of E naught in just a second, but I can also express this as that same constant E naught times 2 over H bar omega C times the momentum operator for the cavity. Okay, and why I say that there is a so in other words, like what's the point of this, right? The electric field is proportional to the momentum operator. Okay. And so our other quantity, which we're going to deal with, the vector potential operator, is going to be proportional to, if anybody'd like to guess, the chat's open. The position operator. Cavity, not potential operator, position operator. Okay. So there are these prefactors, A naught and E naught. So I just wanted to find those. And probably end up adding something to my picture here. So A naught, the magnitude of A naught is going to be square root of Planck's constant over 2 times the cavity frequency times the permittivity of vacuum times the volume of the cavity. And E naught, magnitude associated, oh, and I have a little unit vector here. And E naught, so these are both vectors. Let me make this make this a little harpoon, not a hat, because it's a vector. E naught is 1 over permittivity of free space, or vacuum, times the cavity volume, also times this unit vector. Okay, so back in our picture, right, the unit vector, right, is a vector pointing along z, and it's got unit length. The cavity volume, we can think of as if we've got some separation, which I'll call L, between the mirrors, then V would be equal to that length cubed. Okay. So this is, I want to pause on this point. So let me pause on this picture for just a second. So I've got length separating the 2 mirrors, which I'm calling L, and I'll just call the cavity volume L cubed. Okay, and then I have this vector, this E hat vector, this unit vector, which is pointing along Z. It's basically, sometimes we call this the polarization direction. It's basically the direction along which the electric field points and along which the vector potential points. And it's really, if you want your molecule to interact with those things, right, then something, either the momentum of the molecule or the dipole moment of the molecule needs to, or both need to be oriented along that polarization axis. Okay. Now the other thing is, so we're going to see that basically both representations, the interaction between our systems are going to be proportional to the magnitudes of either A naught or E naught. So let me just write something here, that interaction between light and matter will be scale proportionally with A naught and E naught. So if V, the cavity volume, is in the denominator, that means a smaller volume means a larger interaction. And I will take one more really brief detour to say that, the kinds of cavities that I've drawn with the two parallel mirrors, right, are not actually particularly small cavities, generally speaking, but people do make these, I mean, zoom way in here. These so-called picocavities, where the volume is on the order of, picometers cubed, the very, very tiny volumes, I'll give you large A naught and E naught, right? Because the volume is so tiny. So, all right. I'll make one other brief remark about this, but that'll otherwise kind of conclude the bare cavity Hamiltonian, and then we'll start talking about the interaction. So the other brief remark I'll make, and this is discussed in our notes, so I'll just kind of speak it in words. But it's sort of a kind of getting at, classic problem that you would work if you were taking a class on cavity quantum electrodynamics or quantum optics or something. So you can express the electric field operator in terms of B daggers and B's, and it looks basically like the momentum operator. And so kind of a classic problem that you would work is you'd say, okay, I'm going to take the ground state of the cavity or the empty cavity, and I'm going to find out what's the average electric field. And that is going to work out like an expectation value of the E hat operator with the zero ket. And when you do that calculation, you're going to find that it's equal to 0. And so, you kind of think, well, all right, what's all this like business about, the strong electric field even in an empty cavity? And then, you might even go and say, okay, well, let me go to the first excited state. So 1 photon in the cavity. And then you also find out that the average electric field is 0 for that. And you'd go to like the 10th excited state and you'd find out that the average electric field is also 0 for that. Now, if you have, and I hope that many of you have worked out such a problem in your intro quantum class, if you've ever calculated the expectation value of momentum for the harmonic oscillator, it also works out to be 0 for any energy eigenstate. Ground state, doesn't matter. That doesn't mean that the thing has no momentum or that it's standing still. It just means that its average momentum is 0. Essentially, what you can reason is that because of the symmetry of the problem, like the right traveling part of the vibration is exactly equal in magnitude to the left traveling. And so you get cancellation of the average momentum. This is exactly the reason why you get cancellation of the average electric field. But if you take something like the expectation value of the electric field operator squared, you get a non-zero electric field, even for an empty cavity. And so that another classic calculation you would do is the uncertainty of the electric field in an empty cavity, right? Which is basically the difference between the expectation value of the E squared operator with the expectation value of the E operator squared. And you find out that there's uncertainty in the electric field, even for the ground state. And so this kind of uncertainty in the electric field, even in an empty cavity, is sometimes given the term vacuum fluctuations. And so the really sort of other, besides what I briefly showed you at the very beginning of this session with the slides, where you're modifying chemistry basically by exchanging photons with a molecule. Well, even in the absence of any photons, right, the vacuum of the cavity still has uncertainty in the electric field, which means there's these little electric field fluctuations which can perturb your molecule and lead to interesting effects. So anyway, like I said, you can look in our notes and kind of guided to do such a problem if you desire. All right, So with that, what I want to do next is I want to actually talk about the interaction. And before I do that, I just want to pause really quickly again to see if there's any questions or comments. Good. Yes, very good question. Is E an external electric field? And Ruby, great answer. No, it is the electric field within the cavity. And so in this context, I would you might be tempted to think of it as an external electric field, but really it is the electric field of our system. So like Ruby said, I would consider it intrinsic. And importantly, even if there's no photon there, there's still an electric field. Okay. All right, so let's continue. Okay, so I'll start. So this Hamiltonian that we're going to write down is going to contain both matter terms, cavity terms, and interaction terms. And I think oftentimes people refer to this as the minimal coupling Hamiltonian. Folks will also refer to this as the P dot A Hamiltonian for, I think, reasons that will become clear-ish as we proceed. Yeah, I do think that there's still an interpretation for the position and momentum expectation value for the cavity ground state. So I think you can still think about yeah, actually, I don't know. So actually, that's a really good question, and I'm going to continue to think about that. But I think the clarity comes by associating the electric field and the magnetic field and the vector potential as being proportional to the cavity position and momentum. But let me think if I come up with something more directly related to the momentum and position themselves, I will definitely chime in on that. Thank you for that good question. All right, so where was I? So the Hamiltonian that we're going to write down is sometimes called the P dot A Hamiltonian. And sometimes called the minimal coupling Hamiltonian. I'm just going to use this notation P dot A, and we'll see why that comes about. Okay. So the first thing that I am going to do is this is going to be general in the sense that there can be any number of charged particles that comprise what we're calling our molecule. So I'm just going to have an index I referring to the different charged particles. And there will be capital N different charged particles. And each charged particle is going to have a mass. So I'll write 1/2 mass sub I. And for each charged particle, I will need a momentum operator for that charged particle. So I'm going to write a p hat sub I. And each charged particle has a charge. So I'm going to write a z sub I. And I will remind everybody what these things are in a minute. And here I have the charge of particle I multiplied by the vector potential for my cavity. And I'm just going to assume a single mode for that cavity. So there's a single sort of frequency for a single frequency photon that this cavity supports. But of course, it can support any number of photons. Okay, so that's part of the P dot A Hamiltonian. I also have a potential for all of my charged particles. So this would be a sum over potentials. Let me just plus the cavity, the bare cavity Hamiltonian, which has got that, B dagger B plus 1/2 times H bar omega. Okay, so let's notate a few of these things. So this is mass of, counts all charged particles. So for a molecule, right, I mean electrons and protons, basically. Mass of each. And then this is the charge. And this is the potential experienced by each particle. And really, if it's charged particles, I should have a pairwise potential there, right, for Coulomb interactions and things like that. So these are sort of the new terms that I had to introduce here. So let's now imagine that. And let me also just quickly remark, right, if I have a mass for each charged particle and a momentum operator for each charged particle, then this is not making any kind of assumptions like the Born-Oppenheimer approximation or anything like that. Like every charged particle is a quantum particle. So that's a somewhat general way to write it. But now what I want to do is I just want to be mindful of the fact that I need to make, I have to have some kind of concrete system, and I want it to be relatively simple. So we'll consider the HF molecule. Vibrational motion. Okay, and so what that means, right, is so then that means basically my number of charged particles is going to go to 1, right? Just this effective vibrating HF molecule. And effective mass mu, right? Where we already talked about this. My effective mass is going to be mass of hydrogen over times mass of fluorine over the sum. And my effective charge, right, I'm going to take the dipole, and I've already used mu, so I need a different thing for dipole. I'll take the dipole moment of HF divided by the equilibrium bond length, which I'm just going to call R, EQ. Right, and the idea here is, what is a dipole moment? It's a charge displaced along some distance. So if I want to define some effective charge for this molecule, I take the dipole moment and I divide it by the distance along which the charge is separated, and that gives me some effective charge. Okay, and then I have a momentum operator. It's just the momentum operator that I was dealing with before for HF. I have a potential operator, right? How should I think about the potential operator for HF? Yes, harmonic, yep. Okay. So then what I can do is I can write now for HF, right? I can write down the P dot A Hamiltonian as follows. Oops, sorry. Okay, so I have right here pure cavity term. So this is nothing more than H hat sub C. This is a mixed term. And this is a matter term. Okay. So what let's see, how are we doing time-wise? So one of the things, I guess, let me perhaps not go through this at this moment in detail, but I'll set this up. And if we have some time, we can do this later. I want to make sure we at least get through the transformation part. But this piece right here, I remarked at the very beginning, it can strike me as a little counterintuitive. Like we can expand this thing out if we want, right? And we'll get p hat squared minus 2 z effective p hat dotted into a hat plus z effective squared a hat squared. Okay, so if I just expand that mixed term out, right, I square the whole thing, I get a matter momentum squared minus a 2 times the matter charge times the matter momentum dotted into the vector potential for the cavity plus the matter charge squared times the vector potential operator for the cavity squared. Okay, so and these terms are all important. So let me also label them. this is, in this representation, what we would call the bilinear coupling. And this is what we'll call the diamagnetic term. And it's quadratic in A hat. Okay, so the bilinear coupling is basically linear, right? It's got a p hat to the 1 power times an a hat to the 1 power. So it's linear in both a matter operator and a cavity operator. The diamagnetic term is quadratic in a cavity operator. And so this B matter momentum dotted into the vector potential is the sort of source of one important kind of coupling, and that's why we call this Hamiltonian sometimes the P dot A. But what I wanted to get at is like why, how to think about this coupling, okay? And so what I want to at least show you, right? So if we remember our definition of the magnitude of the vector potential, we've got all of these constants in here. We've got a Planck's constant in the numerator. We've got a 2 times a frequency times a permittivity times a volume, okay? And each of these, most of these things are dimensional, except for 2. 2 is not dimensional, but everything else is dimensional, right? So the Planck's constant has dimensions of mass times length squared times inverse time. And frequency has dimensions of inverse time. And permittivity is a very weird one, but permittivity, I mean, it's very complicated dimensions. Time to the 4th power, electrical current squared, length to the -3, and m to the -1. Okay, so that's so you sort of like deal with all those dimensions in a quotient, and then take the square root, and you get something. Then of course you have charge, multiply this, so z times a naught, right, is, so z is also got dimensions of electrical charge. So when you work all of this out, what you can figure out is that the fundamental dimensions of a charge times the vector potential is a mass times a length times a time inverse, okay? Which is another way of saying this is a momentum. Okay. So what is this interaction doing here, right? It's basically giving me this z times a is giving me a momentum. So I've got a momentum operator for my matter minus a momentum, right? I'm shifting this matter momentum operator by some momentum, which is proportional to the charge of the molecule times the magnitude of the vector potential. And that's all good. So you can think of the vector potential as imparting a momentum to the charge. And then overall, right, every term by term, this thing here has got momentum squared in each term. So I've got a momentum squared over 2 times mass for this whole first term, which is a kinetic energy. Okay, so all of this thing makes sense. That's, I guess, what I'm trying to get at, is that this makes sense dimensionally. And you can think of the vector potential as imparting momentum to your matter that has charge. And when we get to our other representation, where we're thinking about the electric field into the dipole operator, the electric field into a dipole operator is going to give you an energy. So, and the electric field into a charge itself will give you a force. So these are a few things to kind of keep in mind. Okay. All right. I want to rewrite, well, yes, let me collect my thoughts for just a second. Let me rewrite this P dot A Hamiltonian one alternative way, which is only making use of relationships that we've already used. But I won't dwell on this for too long. So if I wanted to write an expression where the interaction terms are making use of the ladder operators, I can do so in the following way. So I can basically realize that I have in the P dot A Hamiltonian my standard matter Hamiltonian, which is a harmonic oscillator, and my standard cavity Hamiltonian, which is another harmonic oscillator, minus this bilinear coupling term, which if I expand both the matter momentum operator and the cavity vector potential, I'm going to end up with an expression for that interaction as follows. Okay, and once again, this term right here, I'm going to call bilinear coupling. And this is the diamagnetic term. And the bilinear coupling, right, it's got A daggers and A's for the matter subsystem and B daggers and B's for the cavity subsystem. So it really is coupling together both pieces in a very explicit way. And it's linear in operators for the matter and the cavity. The diamagnetic term is quadratic in the cavity operator. It only has B daggers and B's in it. Okay. So what we're going to do now, so this is this second way that I've written it. So let me label this 1 and 2. The second way that we've written it is more akin to how we're going to actually implement this Hamiltonian tomorrow in Python code. And essentially what we're going to do is build matrix representations of these ladder operators, and that's going to allow us to just build matrix representations of this Hamiltonian in actually a lot less work than you might imagine. But I want to concentrate on equation 1, or the first way of expressing this Hamiltonian as kind of the motivation for the next piece. And we're about to cross over another hour. So what I'm going to say now is the next section, we're going to introduce unitary transformations. And the goal here will be to go from this P dot A coupling to a D dot E coupling, where what we've done is moved the interaction between the light and matter from occurring through the momentum operator and the vector potential operator to a representation with the dipole operator for the molecule and the electric field operator for the cavity. And there is actually a reason why we would want to do that for molecules, which I'll be happy to explain. But It's been an hour. We've got about 1 more hour to go. So I'm going to pause for about 5 minutes while I drink some water. I'll pause the recording. If there's any questions, it looks like lots of discussion going on, which is great. If there's any other questions you'd like to ask to be addressed for the whole audience, go ahead and chat me, and I'd be happy to discuss them in just a few minutes. All right. Everybody doing okay? Okay. Well, let's proceed. So, all right, here's what I want to do next. What I want to do is I want to just take a hopefully short amount of time to just introduce the sort of basic definitions and properties of unitary operators. And then I want to work out one example of a unitary operator, of a unitary transformation that I hope will kind of paint the main picture of how we're going to get from the P dot A to the D dot E. And yes, so thank you for this question. Is there a C? There's not a C, as Kenny said. No, there is no C. Those C's are for the cavity, so they're little subscripts. So I do apologize. I think my handwriting is going to unfortunately continue to deteriorate as I get a little fatigued, but I will do my very best. Okay. So, so the first thing is, so one other thing, I guess, if you have studied unitary operators, put a check mark up. And if you, this is often not a standard course in the chemistry quantum mechanics sequence. Okay. That is totally fine. That's part of why we're doing what we're doing. Okay, so so basically the basic definition, we have a unitary unitary operators. This is the definition. Its adjoint is its inverse. Okay, so that's the definition. So I have some unitary operator U hat, and if I take the complex conjugate transpose of that operator, it also happens to be equal to the inverse of that operator. Okay, and so then the consequence of this is the following. If I take the unitary operator U and multiply it by its adjoint, that's the same thing, right, as taking U and multiplying it by its inverse. And so that means what I get out is the identity operator, or the identity matrix if these are matrix representations. And this also works if I commute them. So if I do U dagger U, this is also true. Okay. Okay, so great. Why do we care about this? Well, so what we're going to see, few different things. One is that we can apply unitary operators to states. We can also apply unitary operators to other operators. Okay, and when we apply unitary operators to states, we will in general get new states out. but they will share very special relationships with their old states. They will simply be rotated somehow in space, but will not change their length. So sometimes you will hear this said as unitary transformations are norm conserving. They don't change the length of your state. They don't change the probability density associated with your state, but your state may point in a different direction. And that's maybe worth contrasting with what happens if I take a Hermitian operator and act on a state, which happens to be its eigenstate. In that case, I don't rotate my state at all. It points along exactly the same direction, but its length typically changes, right? Its length changes by the amount equal to its eigenvalue. Okay, so we have this notation. I might take the unitary operator U and act on a state. So I'm just going to call this ket psi, and I get a new state back, ket psi prime. And similarly, if I do this to a bra, I just have the same kind of operation, but I'm going to use the adjoint of that unitary operator, so U dagger, and that gives me bra psi prime. Okay. And now the nice thing about this would be if I take, for example, the bracket of psi with itself, if it's right, this is exactly the same thing as the bracket of psi prime with itself, right? Because what I can do is I can expand the bracket of psi prime with itself as the following. Which is equal to the psi and the identity operator psi, right? So these are identical. What else do we have? So other things that we can say is that we can do a transformation on some operator. So if I have some operator, so any operator, which I'll call b hat, right? I can transform this operator to b hat prime in the following way. Basically by taking U acting on b hat and on U dagger. And this will have the property, so this b dagger will have the same eigenvalues as B, and B daggers eigenstates will just be related to the eigenstates of B multiplied, transformed by the unitary operator. So basically, if, for example, B hat has eigenstate psi with eigenvalues beta, then basically that means that the unitary transformed version of B has eigenstates psi prime with eigenvalues beta. Okay, so this is a long way of saying that if I had a Hamiltonian, so let me write this down because this is basically the important point of all of this. So if I have some Hamiltonian H hat and it's got energy eigenvalues E1, E2, dot, dot, dot through En, then I can find some transformed version of that Hamiltonian H hat prime, which is equal to U acting on H hat, acting on U dagger, which also has same eigenvalues. So this can be helpful because oftentimes you can find a unitary transformation which you can act on your Hamiltonian with that transformation, and the resulting Hamiltonian is somehow simpler, meaning it's easier to find the eigenvalues of that resulting transformed Hamiltonian. And if you can then more easily find those eigenvalues, then what you have now found is the eigenvalues of your original Hamiltonian, right? Because you know that the transformation cannot change the eigenvalues. And furthermore, if you find also the eigenstates of that transformed Hamiltonian, they're not the same states, right? But their relationship to the original states are well known, right? You can simply undo the unitary transformation on those states and get yourself the original states of the harder problem to solve. Yeah, it's quite beautiful, and I apologize I did it quite quickly, but there was a link to some videos from this video series, Professor M does Science. They do just an absolutely fantastic job with unitary transformations, and I highly recommend. There's other properties I think probably quickly worth mentioning. One last property worth mentioning, which is also quite easy to show, but I'm just going to mention the property, but it is in our notes. Let's say that I have a unitary transformation acting on some square of an operator, like so. This is basically the same thing as the transformed operator squared. Okay, so in other words, if I have unitary operator acting on the two operators acting on each other, and then sandwich it with U dagger, that's the same thing as U B U dagger U B U dagger, and that can be determined just by inserting the identity that results from U and U dagger. And this is important. We will at least implicitly use that result later. All right, and two other important details that I want to finally share about unitary transformations before we kind of get back to the physics of all of this. So one way so I've just been speaking sort of abstractly about these operators, but so you might ask, well, how can I build a unitary operator? So one way to build a unitary operator by basically taking the exponential of an anti-Hermitian operator and so what's anti-Hermitian? Well, if Hermitian means equal to its own self-adjoint, it's self-adjoint, right? So a Hermitian operator is equal to its adjoint. An anti-Hermitian operator is the opposite of its adjoint. So the adjoint of an anti-Hermitian operator A is equal to the minus of the operator A. Okay, so I can form a unitary operator always through taking the exponential of some anti-Hermitian operator because it will satisfy the following. U dagger will be equal to e to the minus a. which is the same thing as the inverse of u. Okay. And so then this is how we can get to so, right, all of this is just properties up to this point, but this last property gives you a tool that you can use if you do actually want to do something like take an operator B and find its unitary transformation. So this following relationship is called the Baker-Campbell Hausdorff expansion. And so basically what it does is it leverages the fact that if I can write my unitary operators as these exponentials of other operators, then I can also write my transformation in this way, right, in terms of exponentiation of these operators. And so there's a series expansion of an exponential of a number, which it probably is deep in the recesses of everybody's minds. And this series expansion for an exponential can, be generalized to the series expansion for a matrix or an operator. And so when you work this all out for this product of exponentials in this way, what you get is the following. So I'm trying to transform my operator B hat through this operation. And what I get is a whole series of terms which in principle will go on forever, but oftentimes, and we'll hopefully be able to see this quite clearly today. Well, we'll definitely see this quite clearly, at least with one example. Usually, well, no, not, I shouldn't say usually. If you pick your problem carefully enough, vast majority of these commutators will be equal to 0. So this is quite a mouthful, right? But what I have is the original operator here is the first term in this series. I have the second term in the series is the commutator between A and B, where B is the thing I'm trying to transform, and A is the sort of generator of this unitary transformation. I have a second term, which is a nested commutator. So first I have to take this, basically once I do this piece right here, I have the result for a commutator between A and B. So I can just stick that thing in here, right? I've got commutator A and B, and do one more commutator between whatever that thing is and A again. And like I said, if you're lucky, one of these things goes to 0 quite quickly, and then you don't have to compute anything else. Sometimes that's not the case. Okay. So now the last sort of property that I want to say about these things gets more into something practical. So among the sort of several things that unitary transformations are used for in quantum mechanics, one thing that we can use them for is to sort of apply shifts in some observable. And so the example that I want to give is, so let me write that down. Okay, so we can define shifts in observables through unitary transformations on operators. For example, a shift in momentum can be performed by a transformation of the momentum operator okay, and so that's what we're going to do here. And I think the last thing about doing such a operation is, okay, well, how do you design the transformation appropriately for the momentum operator? So it turns out what you're going to do is you're going to define the transformation using sort of the conjugate of the momentum operator, which is the position operator. So this is exactly what we'll do. And this, I do urge you to follow along. I'll try to do this slowly because this is really going to set up the transformation we'll do to the P dot A Hamiltonian. All right, so I'm going to define this unitary operator in the following way. I'm going to define it as e, the exponential of minus the imaginary unit over h bar times some constant, which I'm just going to call p naught. So that's just a constant, times x hat. Okay, and now x hat is an operator. Let me clean up my notation here. So in this nomenclature, right, a hat, the anti-Hermitian operator, is minus I over h bar times some constant, which I'm calling p naught, x hat. Okay, and x hat is the operator. So that x hat operator is conjugate to the momentum operator. So let's see what happens when we apply this thing to the momentum operator. So I'm going to say I'll transform the momentum operator as follows. I'll have u hat on the left, the momentum operator in the middle, and u hat dagger on the right, which is equal to, right, this e to the minus a, no, sorry, e to the a, p hat, e to the minus a. Okay. And so I can just go up to my BCH expansion, right? And I'm just going to substitute p hat for b hat, right? So the first term in my expansion is going to be b hat. And then I am going to add to that, right, the commutator of what is a hat with p hat, right? So a hat is minus I over h bar times this constant p naught, x hat, comma p hat. And then I have an additional term, which for now, I'm simply not going to worry about. Let's just deal with the first commutator, okay? So this first commutator, right, the only thing I actually have to worry about in the commutator are operators, because constants will automatically commute. So I'm going to identify my constants, right, minus I over h bar, p naught, and I'm just going to factor them outside this commutator. And then I have commutator of x hat p hat. And what is this commutator? Does anybody know? Well, we've said it one time before, but I'll forgive everybody for not remembering. This is this commutator is equal to I h bar. So this is sort of the canonical commutation relation between momentum, position and momentum. Okay, so that's great. So now, right, we're in a position to say, okay, I've got p hat minus I over h bar times p naught times I h bar from the commutator plus whatever comes next. Okay, now I want to evaluate this thing, but let me at this point convince you that whatever comes next has to be zero, right? So we already said the only thing we have to worry about in commutators are operators. This commutator x hat p hat becomes a constant, right? No more operators there. So then that means, right, what happens in the second commutator, if a comma b commutator goes to I h bar, then I just have I have a commutator between an operator and a constant, which goes to zero. So the second term goes to zero. That means there's a zero in the third term, right? The third term contains the second term. So there's a zero here. But every other term has to go to zero. So once we find this constant that pops out of the first commutator, we know we're totally done. No more commutators. Okay. So I'm not going to add any dots because I have convinced myself that every subsequent commutator goes to zero. And now I just have to remember how to multiply i's together. So I've got a minus I times an I, which is going to give me a plus 1. And I've got a h bar over h bar, which is going to go to 1. Sorry about that. This thing goes on its own. So overall, right, what I get out of this is I get p hat plus p naught. So my momentum operator has been shifted by some constant p naught. Yes, Arthur, thank you. Okay, so that's the result. So we can go back up here and we can say, okay, this particular transformation on the p hat operator will give us p hat plus p naught. Okay, and that's our result. So this is the unitary transformation of the momentum operator using an operator that contains the position operator. Okay, and so now what I want to do is come back to our p dot a Hamiltonian, which is now almost a whole page before. So now what we essentially can think about doing, right, is we notice we have this operator in this coupling operator, which has got a p hat for the matter minus some constant times a hat from the cavity. And so the question I'm going to pose is, can we design some unitary operator which is going to shift p hat by the amount plus z effective times a hat? And furthermore, what would be the purpose of such an operator? Okay, so let's think about this. Okay, so here's the question. Okay, can I find some transformation that when applied to P minus Z effective A just gives me P hat back? In other words, it would shift this momentum by the amount plus Z effective A to exactly cancel this minus Z effective A. So the answer to that, so I'm asking that question because there's an affirmative answer to that question. And so this is actually a very special operator, a very special transformation, which is called the power Zeno-Woolley operator. I'm going to write it out. And the way to define this thing, UPZW, so people often abbreviate it PZW, is E to the minus I over H bar, Z effective, A hat dot X hat. Okay. And so this is cavity vector potential. And this is the matter position. It is also quite common to write this in a slightly different way. It's totally equivalent. Where this is now the matter dipole operator. Because that's equal to Z effective times X hat. Okay. All right. So let's see what we can do with this by using our BCH transformation. But one of the things, and I think we're going to be able to do it. One of the final things I want to point out, though, before we actually do that. So I expect, just based on what we just did with the p hat operator, right, that this PZW operator is going to shift the matter momentum. And the reason why is because it is using the conjugate of the matter momentum operator, right? It's using the matter position operator. But I'm going to make a similar argument for the cavity momentum. I'm going to assert that this is also going to shift the cavity momentum. And I wonder if anybody can see why that would be the case. And this at least gets to, this doesn't really address the earlier question about the cavity position and momentum operators, but it's connected. So let me just do my scroll up for at least one more time. So the rationale here, right, is that we actually know that the vector potential operator for the cavity is proportional to the position operator for the cavity. So by basically defining our transformation operator in terms of A hat for the cavity, that is going to be the conjugate, that operator will behave like the conjugate of the momentum operator. So it's going to shift the momentum of the cavity. Okay. So sometimes you'll hear the PZW transformation referred to as a double shift operator or a double boost operator, because it's going to shift both the matter momentum and the cavity momentum. Okay. So let's see how this goes. Okay. And then I think we're going to be in a good position to wrap up at that point. Okay. So copy. So here's what I want to do. I want to take U PZW and act on P dot A with it. So I want to transform the entire Hamiltonian okay, but I want to do this as cleanly as possible. So what I'm going to assert again is that this transformation is only going to act, or say only going to transform terms with either with matter and or cavity momentum. Position terms remain unchanged. And that's because if you apply that operator to any terms with a position operator, you're just going to end up with commutators between position operators with themselves. And the position operator will always commute with itself. So you will have no issues. Those terms will remain untransformed. So let's circle, I'm just going to highlight here the terms that we have to worry about, right? All right, term one has got a matter momentum operator. So I've got to worry about term one. Term two has a matter position operator. I don't have to worry about term two. Term three has a cavity momentum operator, so I do have to worry about that. Term four has a cavity position operator, so I don't have to worry about that. All right. So now I'm going to just note, right, that my PZW operator is designed to shift the matter momentum by the amount plus Z effective A, right? And I can basically do that just by realizing that I can make the substitution right in the example I actually worked out. I can just call P naught Z effective A, and then I have defined my PZW operator, right? In other words, the PZW operator could be defined as exactly this unitary operator here, where P naught is defined as Z effective times A hat. Okay. So let's do this. Which we had a relationship already that we can use here. So if I'm transforming the square of this operator, it is the same thing as the square of the transformed operator. That was one of the relationships we very quickly wrote down. And now the sort of sole effect of the PZW on this P hat minus Z effective A is to shift it by plus Z effective A. So we'll write this in the following way. And this cancels with this, and this just gives us P hat squared. Okay. So call this A, right? This is the result for A. And now let's also worry about this one. So now we've got the transformation of the cavity Hamiltonian, the cavity P hat operator just give it this factor of 1/2. We'll remember later that we need that factor of 1/2, or that there's a factor of 1/2 out front. Okay, and so now the question is, well, what should we be shifting the cavity momentum by? And that is a question we need to think about a little bit. Let's look at what yes. I'm sorry, I'm going to cheat. We can figure out why this is the case. There's some constant substitutions that are not going to roll off my tongue at this very moment. Essentially, what we can get is that this transformation on P hat is on the cavity momentum is going to give us the cavity momentum plus 2 times omega c over h bar times mu hat times a naught. So we'll call this term B. Okay. And so all we have to do now is substitute the result for term A and for term B into this equation for the P dot A Hamiltonian. And so let's try to do that. P dot A is equal to P hat squared over 2 mu plus 1/2 K x hat squared plus 1/2 p hat c plus 2 omega c over h bar mu hat dot a naught squared plus 1/2 omega c xc squared. And I'll make one more equivalent representation of this Hamiltonian, again, quite quickly, and then let's wrap up. So this is p hat squared over 2 mu plus 1/2 kx squared. This is the ordinary harmonic oscillator Hamiltonian. Oops. After I've applied this transformation, I'm sorry, I shouldn't have been writing p dot a. I should be now writing d dot e. And this last substitution will hopefully help clear that up. Okay, so this is the ordinary matter Hamiltonian for the harmonic oscillator. So I'll call it h hat sub m. This 1/2 p sub c squared plus 1/2 omega c xc. So basically the term here plus this is the ordinary cavity Hamiltonian. And then what the terms that are left over, there's a cross term, like 1/2 cavity momentum times 2 omega over h bar square root mu dot a naught. This can be written as follows. Oops. So now, because I have the cavity momentum operator into the matter dipole operator, if you remember, the electric field of the cavity is proportional to the cavity momentum. So now I have switched to E hat as the cavity electric field and mu hat as the matter dipole operator. So this is now the bilinear coupling term in this d dot e plus 1/2 mu hat dot e squared. And this is now what's called, this is the next quadratic term that we'll deal with, which is called the quadratic dipole self-energy. Okay, so real quick, what has happened by transforming with the PZW operator? We still have a bilinear coupling term, but now the coupling occurs through the dipole operator of the molecule and the electric field operator of the cavity. And we have lost sorry, this is not an operator. We have lost this quadratic diamagnetic term from the P dot A Hamiltonian and gained this quadratic dipole self-energy term. So both Hamiltonians have a quadratic term that couples things together and linear term that couples things together. The linear term occurs through the momentum and the vector potential and the minimal coupling Hamiltonian, and the dipole moment and the electric field and the d dot e Hamiltonian. The diamagnetic term is in the minimal coupling Hamiltonian and only has cavity operators, and the dipole self-energy is in the d dot e Hamiltonian and only has matter operators. Okay, so I think this is a good place to stop. So I'm going to switch back here to stop share. I'm trying to stop share. Well, maybe I'll just share my screen here. Okay. I don't know what's happening now. So yeah, let's pause there for today, and I'd be happy to address any questions if I can possibly manage to get back to my screen. Okay. All right. Well, if no questions, we'll pick it back up tomorrow at 2 p.m. You should have all gotten a link to the GitHub repository. So you can clone that GitHub repository to get access to that Jupyter notebook. You can probably download it directly from the GitHub repository as well. I think I mentioned in the email, we'll be doing the live coding through a platform called ChenCompute, but there's, any platform that you're comfortable with is totally fine. You can do it on Google Colab or Jupyter Lab or whatever your preference is. If you want to use ChenCompute, I do strongly recommend you make sure you have an account set up before we start tomorrow, because it will just take a minute or two. And I know that if you're enrolled at an institution of higher education in the US, then you should automatically have credentials through your university login. And if not, you may be able to access it through a Google login or similar. Yes, today's video is going to be uploaded. So once it processes, I will actually upload the video to our YouTube channel, and I'll share that link to everybody, and I'll add it to the Google Doc that had resources on it. So yes, video is going to be uploaded for sure. Well, assuming no catastrophic technical difficulties, it will be uploaded. Yeah. Any other questions? Well, I am really grateful to the 18 or so of you that stuck it out for 3 hours. I appreciate your attention and your enthusiasm.
Yeah, thank you. That was awesome. Yeah.
Thank you. All right. Hope to see many of you tomorrow.